The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha, everyone. I am geologist Philip Ong, here with Mr. Dane DuPont from HVERI, the Hawaiian Volcano Education and Resilience Institute. We're happy to have our ASL interpreters once again today. Mahalo, Dano, and Carrie for joining us. And this is the Hawaiian Volcano Tracker, our Hawaiian Islands volcano updates today for Thursday, November 16th, 2023. We're seeing earthquakes still in Kilauea, Dane, pulses of intrusion, inflation, but really the story is very similar to the last few weeks here. What do you think? How have you been?
Yeah, doing good. Been waiting and seeing what it does. It keeps rumbling and let us know it's still active. More or less the same, huh?
Yeah, it's had a little bit of a change, and we'll go through it here, but it's pretty similar to what we've seen. And the question everyone has, of course, that we don't have the answer to is, how long can this last? When will it switch to maybe erupt? And we'll just keep monitoring and keeping pace with what's happening. And it's always a wait and see situation.
Yeah, definitely.
So
yeah, we'll be taking questions in the chat. If you have anything related to the Hawaiian volcanoes that you're curious about, go ahead and drop a question. And if I can answer it, I will. If it's interesting or I might struggle with it, we'll pass it to Phil.
Mahalo, Dane, for leading that discussion on the chat and collecting questions for us. We're going to do our update today in two parts. We're going to do our regular step through the signals as we usually do. And our second part will catch up with our tribute to USGS former scientist in charge, Jim Kauahikaua. Jim K, we'll call him from here forward, for the sake of everyone, including our interpreters here, Jim K. So yeah, he passed last month. It's been about a month. He contributed so much to the research. So it'll really be a little bit of a recap research segment, just highlighting some points. Hopefully it won't take too long, but we'll add that here to the end of our program. And one scheduling note, seeing as 1 week from today is Thanksgiving Thursday, we were planned to skip next week unless something happens at the volcano where we're forced to come back online.
Could happen. So never know.
Yeah, could happen. People have been asking me, at the post office elsewhere, what do I think will happen? And I keep saying, well, it's just really unpredictable. This pattern hasn't been what we've seen on Kilauea for decades, and it could keep filling passively for months and months and months, or it could erupt tomorrow. And either one of those wouldn't be surprising to me, really. Those are both in a range of possibility. So it's a really large unknown of what's going to happen. Interesting to see how the volcano is swelling and growing and filling. And that's basically what's happening as it prepares to either erupt or to stretch and grow underground.
Yep.
All right. So all that said,
get into it.
Let's switch into it here. Let's rearrange our screen for everyone and put up our Hawaiian volcano summary. So our Hawaiian volcano summary this week: Kilauea's earthquakes continue south of the summit and extending down a southwest rift, including a patch furthest away close to the 1823 vents on the far stretches of the southwest rift zone. Also, there's a cluster of earthquakes in this East Rift connector, Upper East Rift Zone is sometimes known. Not necessarily of concern, but part of this long linear feature that is accommodating the expansion of magma in the summit, and then the south flank also moving. And so this is the zone in between that I often describe as an accordion that can fill and compress and adjust to those movements. That's how they look in our map view. Looking at the counts over the last month, here they are for Kilauea, earthquakes per day. So this event began in the beginning of October. So it's 6 weeks ago or so. We're missing the beginning of it on this graph, but you do see this big pulse of earthquakes, which lasted through October 30th. And that had several waxing and waning of seismicity, different pulses within that, call it a surge perhaps. And really, last week, it quieted down significantly to these background levels you see here. Now, within this past week, starting on the 10th, earthquakes have returned, not quite to the same level as before, and not as consistently. So you see one day with a high earthquake count, and the next day with a lower one, and the next one higher, and the next one lower, and so on. It really seems to be a better connected system where magma is coming in, presumably another pulse is coming through, and as it's basically injecting its way into this now open system, causing the earthquakes and ground movement to resume what we saw last month. And illustrating that is the ground tilt from the Sand Hill station. This station has two lines. The blue one points towards Halemaʻumaʻu. The green one points east to the area south of the summit. And this green line is the one that we have heard from the USGS inflated by 120 microradians prior to the 30th here. So in the last week, we've seen this signal inflate on a range of 35 microradians, which is a huge amount. I would expect the ground has risen several inches in that area within this last week again. Not as much as the previous month, but resuming that pattern. And where we saw last week the coincident rise of magma within Halemaʻumaʻu and that southern area, what we've seen in the last week is a reversal of that. So it seems like the Halemaʻumaʻu area seems to be now deflating, losing its magma, and the area south of the summit is once again gaining it. So it's almost like Halemaʻumaʻu is acting like a storage or holding area, and the magma is pressurizing, filling that area first, and then working its way through that network to the south, causing that extra earthquakes and inflation that you're seeing here at the Sandhill Station. If we look at the GPS at the outlet station, that's also nearby, you can see a pattern that's typical of all the areas south, where this panel is showing the up and down motion of the GPS station. It was rising quite rapidly last month, and then slightly slower, and last week it had basically stabilized. And what you're seeing here at this last end is that once again it is rising fairly quickly once again. Because of the scale of this graph being 2 years long and 5 centimeters across these dashes, I can't tell you exactly how much it's risen, but it appears to be several centimeters or a few inches here. So that's the summary for Kilauea. Similar patterns as before, and still waiting to see what comes next. To wrap it up with Mauna Loa, Mauna Loa this month has shown lots of earthquakes, both deep and shallow, but they peaked about 2 weeks ago with a flurry of deeper earthquakes that caused a swarm of shallower earthquakes right around the 2nd or 3rd of November here. So last week, we saw a slowdown of earthquakes following that across all the depths. And really this past week now, we've seen very, very, very few events. There is one slightly larger event that's much shallower at the summit. But those, or I'm sorry, not the summit, it's on a northeast flank. But that's normal to what you see occurring other times with the volcano. So really a big slowdown on Mauna Loa. This pattern of seismicity that occurred recently does suggest that magma is reaching the shallower parts of the volcano and pressurizing, starting to pressurize in there, as evidenced by earthquakes. But it hasn't built to the point where those are constant and concerning, but it is showing the volcano is filling with magma as we approach the 1-year anniversary of its eruption here. That is a summary for Mauna Loa, and it completes our Hawaiian volcano summary for this week. So, stepping through, we like to always talk about volcanic hazards first, because our mission is to improve preparedness on volcanoes through education. And most of the time, the dominant hazard of this volcano is its gas, that even if eruption occurs fully within a national park, the gas will certainly fly out of it and affect communities downwind. So we use this VOG measurement and prediction project website, the VMAP, from University of Hawaii, Manoa, as we look at every week. And they provide this VOG dashboard and forecast. So let's run an animation here. The source of the gas is Kilauea right here. The amount of gas coming out is not great at all, 124 tons per day, which for a volcano is very little. Am I still here? Am I frozen? No, it looks like our interpreter may be frozen.
Yeah, that's I think Dano, we froze on Dano. I think maybe connection lost type of situation might have happened. There we go, he's back. Welcome back. All right.
So there's the VOG forecast for Hawaii Island. Once again, very little VOG coming out for the volcano, but it's a lot for human standards, and people downwind should continue their usual precautions. Okay, let's move on to our monitoring. And we'll show you only a few of the updates. And I'll start off with the one from last week's update on Thursday, and just point out that at that point in time, there were very few earthquakes and not a lot to report during this update. However, at that point in time, there was something here in the rift zone observations. You will note that they still say no unusual activity has been noted along the East Rift Zone right here. They are mentioning the Southwest Rift Zone earthquakes already last week. So this is last week, Thursday. And the following day, last week, Friday, is the beginning of this earthquake swarm. So then note that the seismicity begins on November 10th at around midnight, essentially. And beginning at 5 a.m., there was a small swarm at the summit there, mostly within a caldera. I'll skip down through the monitoring signals we've looked at graphically. But what they do say here, adding into the rift zone observations on Friday, they now start saying there have been several minor episodes of seismicity in the upper east rift zone in the past month, but no unusual activity has been noted along the rest of the east rift zone. And that's the adjustment they've made to the text on the rift zone. That was really it for Friday, and there's nothing really to highlight before giving you guys today's update, which is that the intrusion still continues. They are noting Friday, November 10th as the beginning of this latest episode. And the same outlook. Unrest may continue to wax and wane with changes to the input of magma into the area. Right? Eruptive activity could occur in the near future with little or no warning. That's the same as we've heard for most of the last month, a little longer, in fact, and that hasn't changed. So we are now current. Moving on to our data streams, we'll look at this by time segment this week. So monitoring signals by time, looking at last week. Here are the earthquake counts per day. And you can see this cycle of more and less earthquakes we mentioned earlier. As a reminder, when you look at these plots, the days that are not fully counted on either end, you can't really compare fully. Right? It's not catching the full days of data. Right? So you have to ignore the ends here. But you do still see this cycle up and down, up and down, up and down here. Looking at that same data, but split it out among the depth ranges for that same week of time, it's these orange bands at the top are the shallow earthquakes that we're seeing activate. The deeper section, the blue ones, are really not very persistent this past week, whereas the upper ones are the shallower ones here. So there is one of those pulses, a small break, another pulse, small break, another pulse. Here is our big break that lasted about a week. And you see it didn't stop seismicity completely, it just slowed it substantially. And here it begins again last week. And it tails off here within the last few days, so that today we're back in a quiet zone once again. We'll see how that evolves, whether it comes back up tomorrow or not. But this does correspond to the ground tilt we're seeing at Kilauea Summit. So this is the last week. And what we see here appears to be a typical deflation-inflation cycle, with this first part being the deflation. And we'd expect inflation to come next. So it is thought that this occurs because of movement of magma inside the volcano. It's rearranging itself. So some magma that's heavier will sink down, and other magma that's lighter will rise up. Sometimes they have to move through a narrow space, so they have to take turns. So while one comes down, the volcano deflates, and when the next one comes up, it inflates again. That's more or less simplified version of that process. So this is detecting that change in pressure underground at the summit at Halemaʻumaʻu, and correspondingly, the Southwest Rift and South Caldera earthquakes have also diminished. So there appears to be a pretty good connection right now. And maybe this is because it's been so soon since the most recent intrusion just this last month. The pathway is not closed, it still seems to be open. So when the pressure is increasing, we're seeing extra earthquakes and extra activity on that Southwest Rift area. There's a map we showed earlier. So we'll move it along here to look at the last month. So there is that earlier cycle, the gap, our newest pulse within the last week. This is the same as we described in our summary. And broken out here by depth, as we did earlier, you can see those patterns more compressed. Here is that week-long gap that occurred. And over the last month, the deep earthquakes are a little bit more consistent, as you can see here. All right, so tilt over the last month. We're looking at the Uekahuna Station, UWE. This is in the north part of the caldera. And over the last month, there's been just a slight net gain in our inflation here. But what I see is two different patterns. One that lasts this first 2.5 weeks of the graph, which is basically flat. And it has embedded these deflation-inflation events on it, pretty small ones, right? And then you have this big inflation pulse that comes through just ahead of the earthquakes on the Southwest Rift. And so here is where we see that ramp up at Halemaʻumaʻu. And it's the 10th, remember, right in here, when we see that earthquakes begin on the Southwest Rift. Then we see the summit starting to deflate. And the next day, we see the decrease of earthquakes in the Southwest Rift as well. So interesting correlation there. Right? For comparison, there is that inflation pulse at Sand Hill right there. And then it ends right around in there, as you can see here. Right, the scales of these are pretty different. The scale and tilt here in microradians, you see it's going 0 to 8 at the most, whereas this lower plot is going 0 to 40. And so really this blue line is very similar to the blue line in this plot. It's just really squished down. So that same deflation there corresponds to that inflation there. So interesting pattern to note there. And as we mentioned earlier, there was that previous report, and I'll recall this October 23rd information statement from the USGS. I'm only going to pull one piece of information from here, which is this. In total, approximately 120 microradians of change have been recorded by the Sand Hill tilt meter over the past 3 weeks. Right, so 120 microradians. You see that this entire plot is only 70. So if we could plot all the last 6 weeks, this would appear a much smaller bump compared to what we've seen about 6 weeks ago. And covering the rift zone here, here is a Jonica station showing deflation, everything going down, no changes on the rift zone near people. Our gas hasn't been measured in a while, but it's still low, as all the indicators suggest. And the map of earthquakes for the last month is a lot more busy, as you can see here. You really get a much better idea of the scale of this event and how many earthquakes are occurring along the Southwest Rift here and along this East Rift connector patch and in this lowermost Southwest Rift patch as well. These are accumulating for sure, and they're very striking for the changes occurring in a volcano. Also, more easily visible is the south flank of Kilauea by the East Rift, also showing activity here. So this is the normal background. This whole flank is always trying to move towards the ocean and adjust that way. So you often see that pattern there. So everything is as we've recently seen, as expected. And so to put it in a little more perspective, let's look at the earthquake counts for the last year. Here we are. We're looking at earthquakes per week now. And we are around 300, 400 earthquakes per week for the last 2 weeks, which is down from a peak 3 weeks ago of 1,300. So interesting pattern there. What you can also tell is that we've been in an extended period now of seismicity. This reminds us of the era prior to June 2023, where there was approximately 7-8 weeks of earthquakes before that eruption began. The eruption didn't last long either. The eruption that we had in September seemed to build up for less time than that, perhaps 4 weeks. So we are at the longer end of that right now, right? And so it's tempting to think, okay, we've seen the dynamics of these recent eruptions in the past, and wish we should follow the same pattern. And usually that's the best guess we have to go on. But the fact that we've seen so many earthquakes in that area south of the summit, in a Kauahikaua fault zone, and how it adjusts many times over Kilauea's history without erupting, that's where the questions come in. Could we see a much more extended weeks and weeks and weeks and weeks of seismicity because we're now involving this reservoir that's under the Kauahikaua fault zone? That's the hanging question, and as we keep saying, we'll wait and see. So GPS at the summit is the measure north to south across the caldera. When a magma is building in Halemaʻumaʻu within a caldera, we see this line expand and contract based only on that magma reservoir. But when you have an extra reservoir that's outside of it, to the other side of that measurement stick, it's basically outside the ruler, then we're not capturing the full motion of the volcano. And instead we're capturing just a section reacting to that. So that's why we've seen the pattern on this line for the last year change. Here it is rising, meaning the two sides of the crater are getting further apart. They pop open during an eruption, like right there and like right there, sag back down as the pressure is released and vented, and resume that buildup and pressurization, as you see here. Now you can see since the beginning of October, when we've had this most recent intrusion, this has gotten almost flat, showing that it's basically staying still and adjustments happening outside the caldera. So last week, a couple weeks ago, we saw this change and noted the return of extension from Halemaʻumaʻu. And just last week, this reversed again. So now it seems to be going flat again, or even getting compressed from the south. So similar patterns there as before. And similar patterns in the East Rift Zone where there is no activity, just continued contraction as it sags closer together. So we've been showing you the 2-year GPS signals every week. I will just quickly point out that all the stations are doing what they were doing before, and with little variations like I mentioned in the recent week here. But the stations at the summit are now rising again and getting pushed to the north. The stations south of the caldera are rising and getting pushed from the southwest rift. So usually they're getting pushed from the west to the east and from the north to the south as well. So for example, I'll just once again point out the vertical component of these stations. The outlet, here it is rising, and they all have a similar pattern. It rises quickly, slowly, stops, and then here we go quickly again. So there you see it at the outlet station. Let's go to Ahua. There it is, the same pattern right there. Puhimau, same pattern. You go over to, well, that's mostly what we're going to see because unfortunately other stations are not transmitting data. So this one, these are south flank stations. Hilanapali, which we were looking at closely for many of the last weeks, has stopped transmitting, as well as the station adjacent to it, Ilimakui. So likely something with the transmission is not functioning, and that data will come back online soon. The takeaway message is the patterns are the same as they've been here recently. And one final thing to point out, they are still working on these stations all the time. So here's a station at Muli Vaiopele that's come back online. This is a 2-year plot. So you see it's been offline for all of 2 years. And we'll have to wait for the data to stabilize before it's useful. But great to see the maintenance work ongoing still. Okay, so that's the monitoring data. We'll turn to our earthquakes next and look in a little more detail at the earthquakes themselves. And starting off with our island map, There it is. We have our settling earthquakes around Mauna Kea, Waialae, west flank of Mauna Loa there as well. Mauna Loa's got its few earthquakes here on its northeast flank. Not too many to be concerned about. They're an area adjacent to last year's eruption site and in the area that is between Kilauea Summit and Mauna Loa. So it often shows seismicity. So nothing of concern there. And here we are looking at the Kilauea pattern once again. The most recent earthquakes are occurring still down here, 2.0 on this lower southwest rift area. But many of the earthquakes that are recent are down in the depths here, deep Pahala earthquakes, as you can see. They're harder to separate when they're plotted by, or when they're colored by time. Right? The red ones are in the last 2 hours, the orange ones in the last 2 days, and last 1 hour, last 1 day, and the yellow ones in the last 1 week. But really the depths are what's important here, which is why we come back to this plot where it does color them by depth. So you can distinguish the shallow ones from the deep ones. Okay, so in a little more detail, looking at the USGS website and doing a cross-section across the earthquakes, and I've selected here the full last 6 weeks, so the full event here, and starting off to show you guys the earthquake count. So this is how many counts of earthquakes in that rectangle I drew, and this is the last 6 weeks of time here in the bottom. So how steep this line shows is how fast earthquakes are occurring over time. So they're happening pretty fast, slow, fast, slow, fast, slows down, really fast, pretty fast. There it slows down. Here, this is our week-long gap that we just experienced. And here's the last week right here, where it's shot back up at very high rates of counts once again, with occasional little slowdowns as well, our most recent one here at the top. And that's looking at the full 6 weeks. If we zoom it into just the last 2 weeks, there is that 1 week pause, slowdown, and a more recent ramp up where you can see the pulses. Strong pulse, weaker, strong, weak, strong, weaker, stronger, weaker, as such. So if we zoom it into the last 2 days, for the last 2 days, you can see the counts have been quick and just recently slowing down to lower rates. We can also look at these as depth versus time, right? So looking at the last 2 days, here is how these earthquakes plot. The reason this is useful is if magma is moving towards the surface, you expect to see a progression over time, something like that, right? From depth, as time goes on to the right, the earthquake's getting shallower and shallower and shallower, eventually reaching the surface. That's a progression of magma working its way to the surface. And we don't see that. We're seeing, it looks like essentially random adjustments, like you have the reservoir filling, and it's cracking over here and over there and over here and over there, and it's all happening in a similar range of depth that's not near the surface. This is for the last 2 days. Sometimes we plot these for longer time periods. So for example, here is the last 2 weeks. You have to be careful when you look at these now and compress time that we don't look at this orange blob and say, okay, it looks like it's actually doing that, because we're too zoomed in to see the fine detail there. So on this time scale, these arrows of magma ascension look almost like a straight up and down line. And we're not seeing that here either. We can see that last week, the earthquakes did reach slightly shallower, but there wasn't exactly that progression. Maybe you could say something like this might look like it's working its way. Maybe that was a little pulse that didn't quite make it to the surface. And then we have the main reservoir filling after that. Zoom it out one more time to the full last 6 weeks, and you see similar patterns, right? That first pulse was one of the more concerning ones, pretty vertical ascent there. And then the next one getting pretty shallow here, closest to the surface that we've seen within the last 6 weeks. So in comparison, what's happening now is pretty normal and not to the extreme we saw at the beginning of the event. Okay, so we also can plot, if I pull back this map over here, there's an A and a B drawn on here. So we'll slice through the volcano from A to B and present you with this cross section. So here is A on the left and B on the right. And there is how these earthquakes project along that line. Kind of hard to see, so I've tried to simplify it, but I'm going to take some liberty here and I'll show you this. Or I've superimposed the earthquakes on the cross section of the volcano. Now, this is not exact. This is my best approximation, schematic, if you will, to give you an idea of where these might be more or less. So for the last 2 days, these are all plotted in orange. Might be slightly hard to see in there, but there they are. You see they are to the west of the South Caldera chamber, west of the Halemaʻumaʻu chamber, and somewhat in between the two, extending towards the southwest rift, with occasional deeper and further events away that are not showing up on this plot. Maybe one right here. So that's the last 2 days. For comparison, the last 2 weeks, where you see there was more activity, more widespread, and this activity didn't show up on my last plot, but this is the earthquake we just saw happen at 2.0, so this is still ongoing. And if I show you the last 6 weeks altogether, there is a full range of where this activity is happening. There is a little bit of error here. These earthquakes right here should really all be on this side of the chamber because of my projection. Kind of got flattened, but I'm going to ignore that and just put the caveat for you guys verbally. So there's an idea more or less of where these earthquakes are occurring relative to the magma chambers and the rift zones of volcano, and really focused to the southwest. And that's our dive into the earthquakes here. So we'll quickly recap Mauna Loa, which has been quiet this past week. There has been slight inflation happening there, barely worth mentioning at this scale. Earthquakes, depth versus time. There is one notable one here. Otherwise, a lot of white space on this graph. In comparison, here is the last month. So here's our recent gentle inflation. We have seen adjustments of Mauna Loa. This one corresponded to that earthquake swarm that was pretty shallow. Or the deep one and a shallow one. So here's the deep earthquakes and the shallow ones. Same month of time right there. And here on this month-long plot, you can see how devoid of any activity we are in the last week. Looking at that as the earthquake counts per day, here we are with 0 counts in the last, and 3 of the last, 4 of the last 7 days here. And for comparison, the recent post we saw this month is pretty small compared to what we saw a year ago, just prior to the eruption of Mauna Loa. And for comparison, the last 5 years, here is the last month, and here is the background baseline of buildup for 4 years before that eruption. So we're still below that threshold at this point in time. Pretty quiet on Mauna Loa. There is the map of earthquakes under Mauna Loa for all month. Right there. Colored by depth once again. And for the last week, hardly anything happening here. So that's Mauna Loa. GPS is not really anything new here, so we will go on to our volcano watch for the week. And this week's volcano watch is about fostering preparedness among youth on our island. Fostering preparedness among youth on our island is this week's volcano watch. So this is something that we at HVERI are also getting into. We'll talk about that more in coming months. But the University of Hawaii is a partner of the USGS, along with CSAVE, which is the Center for the Study of Active Volcanoes. And they are based out of the University of Hawaii at Hilo, where they invite school groups to come for demonstrations. Their lead image here is what they call their trash cano, where they're using liquid nitrogen and a bunch of colored balls, and they erupt this thing, and all the colored balls go flying in this area. You see all the students scattered all around watching this demonstration. It's pretty cool to have those resources from UH to show this. So this is part of the work that we're also doing, right? When we don't have an eruption happening, we're educating so that we can better prepare. And children are especially important. Here's a Hawaiian adage. If you plan for a year, plant kalo. If you plan for 10 years, plant koa. If you plan for 100 years, teach the children. So that's the idea here. We want to embed all this knowledge early in our youth so that we don't have the same struggles with eruptions as we've had in recent decades here. So there are outreach events that the USGS and CSAFE puts on, demonstrations showing the kids rocks. That's essentially what this is about. And very important work. The Volcano Watch is posted on hawaiitracker.com and our Facebook group if you'd like to see it further. So that was this week's Volcano Watch. And at this point, I'll turn to the Volcano Watch from last month, honoring Jim Kauahikaua. But maybe before I get into this, I can, Dane, pause and see if there's any questions we want to discuss here on current activity before we get into some of this research topics here.
There was one. Victoria asks about the depth of the lava or the magma. So magma is nowhere near the surface yet. How many miles down roughly? Because we're looking at the earthquake graph. It doesn't exactly show where the lava is, but it's kind of an analog. And then on the previous graph, it had the sea level as well included. So the sea level above, sea level below. So yeah, how far roughly?
So there is this plot right here in the middle. This ruler right here in the middle, which is in kilometers, depth below the surface. So it's counting the surface is 0, and the surface is about 1 kilometer above sea level. So in this plot, where it says 1, that's sea level right there. Okay. So the magma is generally below that, below sea level, but there are storage areas closer to the surface. The shallow chamber under Halemaʻumaʻu is thought to be about 1.5 kilometers down in here, whereas the deeper chamber is in a range of 3 to 5 or so. A pretty tall structure. And also to mention, not depicted on this, we have another magma body right at the surface right here, which is our lava lake, right, that has a good amount of lava in it as well. So that's the closest lava to the surface. If you're talking about storage reservoirs underground, then you're looking at in a range of 1.5 kilometers, half mile or greater below the ground. Yeah.
Right.
Answer Victoria's question.
All right. Yeah, I think that does it for now, and we can go ahead and transition into the next segment.
All right. So we'll do Volcano Watch in honor of Dr. Jim K. So let's pull that up again here. Where is here it is. All right. So this was October 20th, 2023's Volcano Watch. And Jim K was the first Kanaka Maoli, the first indigenous Hawaiian to serve as scientist in charge of USGS HVO. He was also an accomplished scientist and historian as well. Here he is using his VLF, very low frequency measurement technique, to measure lava flowing in lava tubes underground. This is a skylight There's a lava river beneath his feet right here that he's measuring its dimensions with this instrument. We'll get into this here shortly. But Jim grew up on Oahu, attended Kamehameha schools, Pomona College in California, and University of Hawaii at Manoa. He joined HVO in 1988 as a geophysicist, and notably, much of his research were topics that he thought would directly benefit the people of the island. So he starts off measuring electrical resistivity, and this is useful initially to measure groundwater under Kilauea. He does this on Kilauea, in Kona, in the Saddle. This later becomes important when water returns to Halemaʻumaʻu in 2019, following a 2018 collapse. So as an example, here is a paper back from the mid-'80s by Jim Kay, resistivity structure beneath Kilauea. This is before the days of Photoshop and Illustrator, right? So you get these nice old geologic maps here. And what they did was they installed an electrical loop that ran at 80 amps here in, looks like, the golf course area. And then they went to everywhere there's a little asterisk star and measured the resistivity of that source, reflecting off the layers within the volcano. So this map is showing similar to what we saw in cross-section. There's an A to an A prime, a B to a B prime, a C to a C prime. This is the most interesting one because it cuts Mauna Loa across Kilauea caldera to the south flank. You get a D to D prime, and there are the lines. So as an example of what this looked like, here is the A to A prime line. The triangles are where they were taking measurements. And below there is their inferred different layers of resistivity. So usually what you're looking at is this is probably a top of some, very generally, a saltwater layer. So resistivity is measuring really the current, but that's affected by salinity, by temperature, by the porosity of the rock, lots of things like that. Without getting lost in the details, the results were that they found several layers of change underground corresponding to the presence of salt water and increasing temperature with depth under the volcano. They also, at some points, found deep signals that appeared to be the magma bodies themselves. So back to Victoria's question of how deep is the magma. Here they can see under Puhimau crater, it was actually 5 kilometers, about 3 miles deep, right in there, in that particular area. That's A to A prime. Won't go into detail with all of them. There's B to B prime. Let's look at the one that takes Mauna Loa into account as well. So there is a slip of Mauna Loa right there. Here is Halemaʻumaʻu. So northwest of Kilauea, you have a different structure with only one big boundary compared to south of Halemaʻumaʻu, where you see 3 different boundaries. So 2 layers, 4 layers. 1, 2, 3, 4. This one down here would be 5. And there's a magma once again. On this side, you only get 2. So real change across the volcano. And interesting because we talk about the Kauai fault zone. That's this whole zone right over here to the south. That's where all this mess is happening. And you see magma storage down there as well. So that's a little insight into some of that early work. What he found with that study was picking up the signal of magma was a important finding. So then he takes that to near surface lava tubes and using that to measure dimensions of active lava flowing within lava tubes. Using the flow velocities, this information was crucial to calculate changes in eruption rates to the community of Kalapana that was covered by lava in 1990. Right, and that destruction in Kalapana of a Hawaiian community, you can imagine it must have resonated very strongly with him. And so from that point forward, he's very strongly interested in lava flow hazards and mitigation. for the rest of his career here as well. So active lava flowing through tubes. We've showed you this picture up here above. That's what he's doing right here. But let me show you a little bit of that work as well. Let's show you this one first. 1995. This is the demise of Kupaeanaha, which was the vent east of Pu'o'o, which erupted for 6 years. And that's the source vent that destroyed Kalapana, July 86 to February 92. And so we'll just scroll down through here to show you what's going on. There is a flow field at the time. Pu'o'o is over here. Kupaeanaha is over here. The Waha'ulu lava tube all the way to the ocean. Destroyed the visitor center at Waha'ula National Park in 1992, I believe, as well as the Heiau, the Hawaiian temple that was there. So there it is in 1985. Now over here is what's actually going on. So here's what the data actually looks like. And maybe I can find the text. Here we go. This is how it actually works. A global network of high-powered military transmitters regularly transmit energy in a VLF range. The radiation from these transmitters combines, I'll summarize here, combines with that created by a lava tube, which is a cylindrical conductor. Ultimately, what happens is the lava, because it's enriched in iron, as it moves and flows, it creates its own electromagnetic field. And if it's in a geometry like a cylinder, like a lava tube, then it creates a disturbance to the electrical field that is present on the surface. So for us, it turns out that out of Pearl Harbor, there is a signal that's sent out to help synchronize all the ships in the Navy. And that's the strongest electrical signal we can detect on Kilauea's coastal plain. And in fact, that's the distortion of that signal was what Jim Kay was measuring to detect how wide the tube was underground in particular. You can look through the hole of the skylight and see how fast it's moving. But without knowing what the cross-section was of the flow going through there, you can't get to a volume. And so by measuring just this cross-section through this innovative technique, he was then able to produce flow rates for the first time with this technique, and a more accurate way of doing that than other times in the past. So what's happening there is the polarization of electricity is changing from we'll call it normal in a perimeter of a lava tube. The lava tube is a combination of conductive lava and hot gas within a elongated ellipse shape. And as you come across these boundaries, you see distortion of the polarization. Right? So what the data actually looks like is like this. Let's see here if I can get it a little smaller. Okay, so you walk across a transect across the lava tube with distance along the bottom here. And you just look through that little instrument and you measure the angle, the tilt angle to measure the distortion of that polarization. And the bottom line is you see that this thing changes right there and right there. And those are the boundaries of your lava tube. And then the actual magnitude can give you some information as well about how much lava is flowing through there. So it gets pretty complicated. I'll leave it at that, but pretty novel for him to devise a technique and deploy it to document the ending of that phase of lava moving through Kalapana. So he takes it a lot further from there. Observations of basaltic lava streams and tubes from Kilauea volcano, where he's a lead author here. This is from 1998, a few years later, and a lot of stuff through here. So I'll just highlight once again the kinds of things that he, as part of the HVO team, was helping document. By these few years later, you can see new lava tubes forming at different points of the flow field. That last paper was showing this one over here, right there. So the eruption is evolving. This eruption was to last 35 years ultimately. And they measured lots of different skylights. A skylight is a hole in a lava tube where you can look through and see that lava flowing underground. And some of these skylights were very long lasting. Here, this 2,500 foot elevation one lasted 4.5 years. You see, there's a whole bunch of these 4.5 years, 4.5 years, 4 years. There's a little gap lower down on a slope, 1.5 years or half a year, but these can last a long time. You see they're measuring slope, the height, the width, velocity of the lava tube, cross-section of the area from VLF, very low frequency measurement there. And from that, they can get then the eruption rates. And then you can say, okay, the rate's going up, the rate's going down, and make inferences about what the volcano is doing underground based on that. Okay, this is, I'm going to skip past the shattering here. This is a long paper. They start taking pictures of lava flows as they progress. So here is a lava flow moving across ground in a flat profile, much wider than it is tall. And as a flow advances and hardens on the outside, but keeps flowing on the inside, it swells. That's also called inflation. Different inflation from the tilt plots we've talked about, but a swelling like a loaf of bread, inflating, rising up. And this was later to be documented through time lapse, but these were the first photographs documenting that process that would lead to that work. The creation of tumuli. A tumulus is like a big lump that's like almost like, looks like a ball almost sticking out of the rock on a flow field. It's the same root as tumor, right? So tumulus, it's like a big growth that comes out of the lava, pops up, and the rocks are usually very thick on the outside, so they make these big, tall ramps, right? So they documented the creation of those, how those are later stage features. Not only does that whole lava flow swell, inflate like a loaf of bread, as it hardens, certain parts of it can then pop up further as these tumuli. Features like, can't really see too well in these black and white images here, but they're in there. Here is their plot of how tall these tumuli can get. 12 feet, right? Talking about 30 feet tall structures, or that upper crust. Oh, I'm sorry, not 12 feet, 12 meters tall. So you're looking at what, 40, 50 feet tall there, right? Or that upper part you're looking at might be 6 meters, 18 feet. You have a little bit of melt in the middle there, right? Maybe 6 feet of it, and you have another 8 feet there below of solid rock too. They documented how this changed over time with fluid in the interior for over a year here. So really interesting stuff. They were monitoring a lava tube that was feeding this, and when the lava no longer comes into the tube, then the process basically comes to an end here. Those are cool things they looked at by following lava tubes and studying them. Here is a little bit more graphical representation of how this thing grew from a fairly flat shape to eventually a big lump there over the flow field. Okay, velocity of lava. What's happening with lava in lava tubes? Is it melting the tube? Is it carving its way down? Is it hardening and sticking to the sides and actually congealing it and constricting the tube, making it smaller? I think all those things have been shown that they could happen, but whether they do happen in any particular case is hard to figure out. And they got some information out of this here, out of looking at lava tubes as well. I'm going to switch our tag here to research, since we're transitioning here into more of that, really. So they noted looking in lava, looking in skylights. Let's see if I can rotate this around enough to put it on the screen here. All right, look, that's what a skylight looks like. You see some flow lines in here. They actually describe a standing wave within here, right there, a standing wave. It's probably hard to see in the red, but they say the lava is coming in from this direction and then making an 80-degree bend off that way. So there's a standing wave that's curling to the left here, dropping to a lower bed of the lava channel underground here. An example of what that looks like. And this is a famous image. There's a color version of it of Jim Kay here with construction grade rebar, sticking it into the lava channel. And the point of this is to figure out the depth, right? So you want to know how far down the lava is within that pit. And this was a way that they would do it. Poking the bottom, see how much it gets covered. And so by measuring those depths, they could then see how that changed compared to the surface, whether the ground was really getting cut down or rising up or what have you. And here are the results of that, right? People have often asked, like, what's really happening in there? So they had a breakout on a particular day that made a new skylight. It looked like this. There is a skylight. There's a lava depth right there, right near the top. Right? You can see some shiny lava where it probably overflowed this hole before receding just below the lip right here. Yeah, there's Laszlo. It's very subtle here. Hand blocking the heat. So he actually is not the heat coming out of these chimneys of lava is intense. I've been about this far away before and had my eyebrows singed off just from the changing wind. So a little subtle block your face from the radiant heat right there. The lava is this close to the surface. Even if it's not, the heat coming out is still immense. So that's the very first day, first few days there. And what they measured over time was the actual rim of the skylight did not change elevation, but the depth of the channel did change. And it did so for the whole length of that breakout being active, several months in 1994. And so the depth went from 1.5 meters to 2 meters to 3 meters to 5 meters over time. And on average, it was cutting down 10 centimeters per day. That's about, 3 to 4 inches every day. So that's really showing how fast it actually can happen. Lava flows can cut down in lava tubes very, very quickly. It got to a depth of 5 meters from May to June. Yeah, that's pretty fast. So that's thought to be a physical erosion. The lava is physically rubbing against the bottom of the lava tube and carving a canyon out below it. That's how it's getting deeper. So this was really the study that showed it. Before this, no one really knew. So there is the initial week. Lava is very shallow. And here it is a month later. There is that same lava surface, a little bump right there. The lava was all up to here before. Now you see its lower bench right through here. A lower bench below that, and there is a lava channel crusted over within the tube itself, way down there, 5 meters down, 16, 18 feet or so. It's really cool stuff there. They also started measuring lava flows down the slopes here. So there you have breakouts of lava tubes down the slope. They look at old examples of downcutting of lava tubes. So here's an example from the Kalapana Sea Cliff area. This right here is the shape of a lava tube. Right there. Goes like that. Okay, all right. Now what's noteworthy about this is where these arrows are pointing, that layer right there seems to be the bottom of the flow right there. And the other one, if I can get back around here, the other bottom of the flow seems to be over here, which is showing you that this channel is actually cutting down, eroding into the flow below it. That's the important thing here. There are more examples than just what they saw poking rebar in a hole. That's an example from Kalapana. There's another example here. This is from Mauna Loa tube. This is down near Whittington Park. And there is that shape of the lava tube right there. Note the lava tubes are gonna capture whatever lava was left in there, still draining out as it hardens. So you see this is the bottom part of this tube is filled with the last bit that was draining out. It has that shape, that oval shape. And here are the edges of that flow as interpreted by these authors. So another down carving example of the channel there. The other thing I noted was how these shapes changed. We talked about how the first flow that comes out over flat ground is very wide and not very tall. And over time, it becomes more oval, and eventually it becomes more circular, and ultimately it ends up being elongated in an up and down fashion like this. So this is something else that they noted through this study of lava tubes as well. So that is a lot of stuff on lava tubes. I'll leave it at that. That was one of Dr. Jim Kay's things, of course, so it's just fair to share it to that level here. All right. He then, continuing, focuses on internal structure of volcanoes. So as a geophysicist, he expands from using just resistivity to starting to measure gravity as well. So a decade-long project measuring gravity across all Hawaii Island produced the results of where the magma is collecting underground on all the volcanoes. So what does that look like? There it is. Deep magmatic structures of Hawaiian volcanoes. And every little black dot on this map is a place they went and sampled. And every gray line on the ocean is somewhere they sampled by ship. So they went all over the place measuring gravity, everywhere they could. And to cut to the chase here, the gravity map looks like this. You can see the shape of the island shaded in the background there. And otherwise, you're seeing these lumps of where there's the most gravity. And in many areas, they correspond to our volcanoes. So this is where Mauna Loa sits. And this is the Southwest Rift. And here's its Northeast Rift. And that's Kilauea. And there's Kilauea's East Rift, all the way offshore. All right, and there's Mauna Kea. There's Kohala. And Kohala, looks like it has a rift going offshore right here as well. You can see through the gravity, right? Hualalai, with an elongated to the south. So you see a lot of internal structure here. And they've actually redrawn this. It's not the best resolution in this paper that I have here, but there you can see it, right? Where they've colored the different summit of Mauna Loa, the rift zones, Kilauea, its rift zones, Hualalai, Mauna Kea, Kohala there, and really showing how the gravity is higher in these areas because dikes are injecting from the magma pathways and hardening underground deep enough to not form any bubbles. That's the key thing. When you don't have bubbles in your rock, they end up being more dense, more mass, more gravity. And so therefore, areas that have more injections end up having higher gravity. Very, very small amounts, but they are able to measure that with their instrumentation. So another one of the really fascinating things here that really uncovered that inner structure of the island, led by Jim Kay here. That's one of my favorites. Moving on, I will say here that he was scientist in charge of the USGS HVO. Right, so let's come back to our volcano watch here. He was the first scientist in charge, one of the longest in HVO's history, from 2004 to 15. As a result, he was awarded the USGS and Department of the Interior Citation for Meritorious Service. Here he is in Washington, D.C., receiving his award with his wife, doing outreach during events on Kilauea during that time, interviews for the media, including documentaries. But the highlight of that, from the public's perspective, was the Pahoa lava flow crisis of 2014-15, for which Jim Kay was scientist in charge. So much of the communication strategy that we use today is rooted in this information that came out back and then. In fact, Hawaii Tracker itself began during this same lava flow crisis as a way to share information on social media. This is something that they pointed out in their assessment of how important that was. And that, through several fits and starts, has eventually led us to where we are today. And so I won't go into too much detail of this, but he was in charge. They made a lot of maps. Those of you guys who were not around in 2014 and 15 or not following us or not knowing what's happening, the summary is that Pu'o was erupting. There had been a disruption at the vent that caused a new fissure on its north side that made a new flow called the Kilauea flow that went around the north side of the rift zone, encountered a crack where it moved through the forest about 4 miles through the crack before re-emerging and then flowing downhill towards Pahoa through the Kauahikaua Homestead subdivision first. Okay, that's the summary of that event, 2014 and 15. The USGS held many community meetings. They made many maps. They did flow predictions. All this informed by what they saw in 1990 in Kalapana. And if you haven't seen these images, this is Kalapana 1990, right there. Here's a flow coming down. There is this high piece of land called a horst over here by the ocean. The lava flow comes and hits this, diverts through the hot springs. The Queen's Bath was back in here and covers that treasure of Kalapana. Here's how it looked in the next photograph and after it was all done right there. And so that informs a lot of this work in 2014 and 15. So this is when we first saw these lines of steepest descent coming into play here in the maps, where you can project, okay, the flow is right over here. If it follows this path, it should follow this line of steepest descent. Most times, because lava is not exactly water, it does create its own topography and can divert where it's going as well. So that was the first time we saw this. Those accurates turned out to be, those estimates, forecasts turned out to be very accurate as far as where it would go. What was not accurate was how fast it would get there. And
right.
That was their main challenge they had during that eruption. And that's
I remember
here as well.
During that period, that was the most frustrating part, was the estimations, because people would just snapshot like, oh, it traveled 600 yards yesterday, therefore in a week it'll go this far. And by the time you've said that, you're already wrong, because it's already changed.
Right.
And it's complete. It was just so frustrating because it changed the entire time.
Here is that crack right there, the lava flow. When it entered the crack right around here, there was a skylight, and it moved through this forest with just steam marking its path through the forest before it emerged above Pahoa. As this began, there were community meetings that happened very frequently in Pahoa, every few days, in fact. And here is one of those outreach events. Here is an example of some of the flow forecasting they did, right? So when a flow front was still above Kauahikaua, here is your lines of steepest descent. They do numerical modeling, and where the flow where it goes most of the time, they color red and then yellow, and then eventually the background. So early on, September 8th, they forecast it could go one of two ways. It could go a little bit north outside of town, or it could go right towards the heart of town. 3 days later, the flow advances, takes a slight turn, and they can say, okay, well, from here, much more likely it's going through town. So you can see how that's not conclusive about when it's going to get there, but it can certainly help emergency managers to respond, evacuate, monitor, all the things they need to do. So this was really the first time in Hawaii that this had been deployed. Right, their strategy involves their daily updates, their website, their Volcano Watch articles, their community meetings, all those things. Lots of pictures online. Here's a little more examples of that. Here's the progression, November 24th, December 1st. Right, in case you were not following back then, there were two branches. The first branch did come to Pahoa, stalled out, broke back up an upslope, and then actually took that second branch as well. And that came behind Pahoa Marketplace. The old Mala Market area was evacuated. but the flow did not quite get that far to the marketplace. Stopped just short.
Also,
Right?
maybe
This is when I really start putting in this alert level scale, color code scale that began under Jim's watch. Volcanic activity notices, information statements, aviation notices, all that protocol got fleshed out during this episode here. And yeah, there's more examples of those maps. And there is a section in here I can point out what their contact for the EOC right there. Geologists as a media liaison, they actually having an equivalent of a PIO for the USGS, someone who was doing education and coordinating all the events. Media briefings that they also had, which were important because they actually prevented media access to lava flow. Media were not allowed to go out there. Here is an image of one of those community meetings. They're at the school in Pahoa. Helicopter overflights, public radio announcements, remote command centers, alternate road planning, construction. They actually did a good amount of that. They actually had student tours, right? So here, where they clearly put out as a first point of discussion, forecast of lava flow paths better than travel times. So they get it. And you can see that they haven't issued times ever since then. Even during Mauna Loa, when lava was approaching Saddle Road, they intentionally avoided saying when it would arrive there, having gone through this experience.
And somehow the media still found a way to snapshot an estimate that didn't really exist of that 2 days. Oh, it'll be at the road in 2 days. Like, where is this based off of? Oh, we wanted to head like that, basically.
They never said that, and this is why. And this is why how you know they did it intentionally, right? It's all very thought out here. Lava diversion was an issue there. Communication, how important communication was to everything, right? Including the role of social media in here. So that was an important part of his career here, more recent. And then he really transitions to more of a historian role. And so I'll just point out some of the publications he was involved with. This one, the first 100 years of the USGS HVO, for which he is second author, along with Janet Babb and Bob Tilling as well here. We did several other variations of this, so really going into the history of the observatory and the science. Yeah, so history of the observatory and the science here is what really Jim was going through. I'll point out this other publication he led in 2019, the lava flow that came to Hilo, the 1880-81 eruption of Mauna Loa volcano, island of Hawaii, which uses a lot of these old art as well. So Jim Kauahikaua, Ben Gaddis, Ku'ule Kanahele, Ken Hahn, and Valerie Wasser. That's awesome there. Seeing Kanahele's name here, I forgot to throw this in here, but Jim K was also the one who convened the Conversing with Pelehonuamea workshop, where he brought together the Hawaiian scientists and the Hawaiian culture practitioners so they could exchange knowledge and really share their perspectives of the history and processes of Kilauea, right? And it's really important because the written record on Kilauea only goes back to 1912 for the volcano. So really everything prior to that is informed by the oral history. So that was really important. This paper, the flow that came to Hilo. We've talked about this before, and we'll come back to it again. And another one we've discussed in the past as well that Jim was involved with as well. Have humans influenced volcanic activity on the lower east rift zone of Kilauea volcano? The short answer is no. Their answer is no, that hasn't happened. Not to say that it couldn't happen, but there's so many other things happening in this area of the volcano, and they go through all the history of what happened before people were here, the range of what's normal, and what we saw in 2018 is within the range of what's normal. And This is a whole other topic on its own, so I won't go off on a tangent right here. Just to say that there he is, Jim Kauahikaua and Frank Truesdell, authors of this report. And those are the ones that I've chosen to highlight for you guys. But if you look somewhere like ResearchGate, which compiles all the publication and work that Jim has done over his whole career, you can see a lot of other things here as well, right? So some of these are not dated, but monitoring volcanic processes with electrical and magnetic methods, emplacement of flows, electrical soundings, potential observations. He's working on Hawaii, on Maui, on Oahu. He actually goes to Nevada at one point as well. Now, he does work because of the groundwater connection on mapping potential hot groundwater as sources of geothermal power back to 1975 when he's doing this. Yeah. More electrical studies, geothermal studies, heat studies. See, for the whole state of Hawaii, geothermal assessments. Not the lead author, but working with Don Thomas and other University of Hawaii researchers. Here is his Nevada test site work in 1981. More geothermal, resistivity, self-potential, salinity beneath groundwater, volcanology with hazards. You see the early years here, a lot more on the electrical and groundwater stuff before you see Kalapana burn down. Then you start seeing more Kalapana flow field, Pahoehoe flow sheets. How did lava change, right? You see early adoption of GIS back in the early 90s, using GIS for geothermal mapping, groundwater studies, GIS for lava flow hazards back in 1995. More lava flow eruptions to Kalapana, Pu'okupainaha. The one we looked at here. Groundwater, gas and lava flows. More eruptions, more eruptions. Start going a little faster here. Gravity of Kona. Eruptions of Pu'o'o. Lava streams. Texture of Pahoehoe and A'a. Cooling and crystallization of Pahoehoe and A'a. Eruptions of Hualalai. So much that
Hawaii one's a good one. Yeah, that Hawaii one I liked in the 1880, 1881 eruption. That was so convenient because I remember I was doing research on that eruption and they published that, released it publicly while I was doing that research. And it was like, oh, this is exactly what I've been looking for and why I've been going down this rabbit hole is that it's not compiled and all in one place.
Yeah, and that work began in 2002. So he's been, I think that was a third version of that product that came out recently. Yeah, there was a VLF, right, for lava effusion rates. That was the big thing there at the time. Right? Linked to the gas scientists there as well. Pu'o'o, microgravity, rise and fall of Pu'o'o, Pahoehoe transition, more flows, instability of lava deltas, magma in the rift zone, landslides from Maui and Haleakala. So many topics here. Atahana is over in the Marianas Trench in the West Pacific, going to monitor volcanoes there. So I'll scroll through some more here. After the intrusion of 2005 under Mauna Loa, they used gravity to confirm the intrusion and estimate volumes there. They've mapped lava tubes. There's how lava flow channels evolve from 59 eruption of Mauna Loa. And then all the way to the current activity, the lava lake in 2008-18, the collapse in 2018, all of that, right? So getting into more of the history here, some more culture, Pahoa 2014 and 15. You can see I'm still going. How many papers does this guy put out? Communication strategies, Kilauea Iki, magnetism, 2018. And all that comes back around. Eruptions at the summit of Kilauea in the 1800s. The return of water to Kilauea following 2018. Chiming in on rainfall being an unlikely factor in a 2018 rift eruption.
Responding to our friends in Florida.
Yeah. Important researchers in Florida, but I think that one was a little off the mark. And most recently, MT investigations of Kilauea. This is publishing data back from the early 2000s, but in anticipation of that survey that just happened last summer here, that will give us the new round of results to complement that. So really, a lot of the foundational work for what we know about Kilauea is what really made Jim's career here, right? So a lot of stuff in here. We're to the point now where we're iterating and learning more about those things, but when he began, we really knew so much less than now. So this really is a tribute to this fantastic career and impact and contribution to Hawaii Island disaster preparedness, response, education here at Hawaii Island. So that was a lot for the research. I know we're running along, but I wanted to give this tribute. I know we're not going to be here next week, but I'll finish it off as usual with our community corner. So let's find that for you guys here. It should be noted that in a national park, that Mauna Iki and Kau Desert trails are still closed due to the volcanic unrest. If you are looking at the park for recreation here in the upcoming months, they will start issuing backcountry camping permits online. Hooray! For the first time starting in December next month. For example, Halape Beach, one of the remote campgrounds you will be able to book online from next month. So just a quick announcement for that. As far as events in the national park, in November, we have one After Dark in the Park left next week, Tuesday, the 21st. Wood turning in Hawaii, a rich Hawaiian tradition. And so they're using wooden bowls and shaping them with tools from coral, lava, or pumice stone, using shark or stingray skins to finish the surface. So it should be interesting stuff. And other regularly scheduled events. And then to turn to December, still a couple weeks away, but it's worth mentioning that December 2nd are the holidays in Kahuku. December 2nd, Saturday, 9 a.m. to 3 p.m. with lots of food and music and crafts and all that. So that's coming up December 2nd in Kahuku. And then most of the events in the park for December are holiday concerts with some other talks in there as well. So we'll come back to that next month. And a little bonus image of the iliahi, the Hawaiian sandalwood flowers here. So those are our community events. And one last thing to mention is that this week was the anniversary, a couple of days ago, the 14th, of the Kilauea eruption. Would have been the 64th anniversary. And 4 years ago, we were able to record this talk by Don Swanson at After Dark in the Park on the Kilauea eruption. So we can drop that link in the chat for you guys here. If you would like more content, go and check this out. Look for our old stuff. There's all kinds of stuff we have online if you guys are missing us next week, for example, where we're all getting fat and sleepy. So that is it for the week, Dane. I'm ready to pass it to you for some mahalos and discussion.
All right. Well, thanks everybody for tuning in today. A little bit of a longer segment, but as Phil said, we won't be here next week. Thanksgiving and all that fun. We want to thank everybody for tuning in. Views, your likes, subscriptions, all that stuff really does help with the algorithm and get this content out there. We don't have an advertising budget. We rely on word of mouth, and all that stuff really does go a long ways. We also do take donations on hberry.org/donate. We've had a bunch of donations come through there in recent weeks, and we want to thank everybody that's made that donation through the website. We also do take the super chats, in which case we did have one come through from Sajid Ed, continued supporter there. Just a super stat sticker, $20 he donated. Appreciate the support there. And yeah,
Yeah. At
Go
some
ahead.
point, we'll catch up, and maybe we'll be able to read off some of those donors through our website as well. But we just haven't.
Maybe.
We've been so
Yeah.
busy, we haven't had a chance to compile them. We see you guys. We see your messages. Mahalo so much.
Yeah.
And we will recognize you. I promise.
Yeah, hopefully we get a little bit more time after Thanksgiving type of thing to be able to catch up on that kind of stuff. But yeah, we don't really have that much in the way of questions. I did have one question for you. We'll throw it out there. So about 4 years ago, we were doing our updates, and we were talking at the time about how 2018 eruption for that rift zone might have meant that rift zone closes up, and then the southwest rift zone activates, going in like a wave motion from one side of the south flank movement, and then it goes to the other. Is that still a working idea, or has that been kind of shelved? Or because it kind of seems like that's what's been playing out over the last few years.
Yeah, that's always been something that we've discussed amongst ourselves. I haven't seen that really written down and published as such anywhere, right? It's our working model, and it does seem to still hold. Absolutely, right? And to recap for you guys, we've mentioned the southwest rift of Kilauea goes off this way. The southeast rift goes off this way. We've mentioned this triangle right in here, right? And how really this whole south flank, it wants to move by gravity south in that direction, right? The problem is it's not one big coherent block. So it's like in different segments. It's like there's a segment, and there's a segment, and there's a segment, and there's a segment. So each one will move slightly independently. And what we saw in 2018 was through the injection of magma through the rift zone, this area right in here moved a lot. And this area didn't move as much, right? So it got torqued. And you'd imagine that in that case, you might want to long-term fix that. And the way to do that is by pushing it further out over here some more. I'm simplifying a lot.
Yeah.
But I'm trying to make it as basic as possible.
You're flushing it out pretty good.
Yeah. So in that case, right, we've seen the stalling and the closing of the rift zone because it's basically had enough space already. It doesn't need to stretch anymore. It can just sit there and sag until magma is ready to push its way back through. But on the other side, that's where it's out of balance, right? So as the summit's building up and it can't come into this zone as easily, then naturally it's going to come through here. And if it does that, then naturally it's going to push this piece of land, and that's trying to catch up to here, right? And because really, this whole south flank is one big structural grain. That's the east rift zone right there. Here it becomes the Kauai rift zone, or the Kauai fault, and then here it becomes the southwest rift, right? It's really all one big structural grain with segments in between it. So this is a segment we're seeing moving right now. Yeah.
I guess the follow-up to that would be, when 2018 we saw when the eruption happened, the south flank was already moving, but it really got kicked on the May 4th with the magnitude 6.9 that happened. If we are going into an eruptive sequence of some kind on the southwest rift zone, which we have heard, being talked about, what are the expectations for another large earthquake, say over magnitude 6 type of thing? Is it a possibility, more than a little bit higher than likely, or just not worth considering?
I mean, it's always possible, right? But it's hard to put any likelihood on it at all. Right. And the reason is because there's so many factors involved. You have Mauna Loa as a huge factor off to the northwest there, influencing the pressure that's just in the rocks everywhere around there.
Right.
That's one important thing here. It's
a complex area.
Yeah, it's complicated. I'm not sure where to take it from there right now. But yeah, it's what's really interesting is these earthquakes all the way down here, right? So we're talking about the whole thing adjusting. And we know that the Kauai fault zone is this orientation like this. It's really showing an adjustment of that whole flank right there, right? We have seen when Mauna Loa erupted in 1868 that it had an earthquake on its flank of 7.9 that then induced a 7.0 around here. So we know that this area can generate large earthquakes, but can it do it if Mauna Loa is not involved is the question.
Right.
We'd have to, it probably depends on the exact
find out.
situation, right? Mauna Loa is not just sitting there, she's also inflating right now.
Right. We did put out the poll again. We put it out, I think maybe 2 weeks ago. At this point was the first time we put it out, with the over under of December 31st for an eruption to take place on Kilauea, anywhere on Kilauea. The under is losing a little bit of favor, but it's still the strong lead at 68%, taking the before December 31st, the under. So we'll see how that progresses. But the only reason December 31st, it's an arbitrary date, but it would make the date for 4 eruptions this year on Kilauea if it were to happen by then. We get our 4th quarter eruption. So we will see, just something we've been keeping track of.
One last thing I mentioned, Dane, I hope you can still hear me, even though I think I'm frozen on the screen here.
Yeah, you are.
So there was the 1823 eruption. That's then on that cluster, that's orange cluster of earthquakes on the left part of the screen. If you guys can still see the screen, I don't know. That area, that 1823 eruption, came out of the Great Crack and was accompanied by some collapse at the summit as well, right? So there is also evidence from that era of essentially a similar crack opening, the magma draining from the summit, coming out of a crack at low elevation and flowing, in that case, all the way to the ocean as well in 1823. That's the closest model we have to 2008.
Okay, we just lost. Yeah, well, there. That's that happened. All right. I think we were at the end of the stream anyways. I think since we lost both Phil and Lou on the back end, that means that probably the internet's having issues up their way. I'm on a slightly different line. So I think that'll do it for this week. We got through it all. Thanks everybody for tuning in today. Just a reminder, next Thursday we will be off for Thanksgiving unless something happens. If we get an eruption, an intrusion that's strong, we'll probably come online and go through it immediately and talk about what's happening. But unless that happens, we will see you in 2 weeks. We'd like to thank our interpreters, Dano and Carrie, for stepping in today and helping us with the ASL interpretation. I will say it was a great enjoyment to see Dano do the interpretation for Phil being frozen on stream. That was actually, it made me laugh. So yeah, thanks everybody for tuning in today. I appreciate you, Dano. I appreciate Carrie. Thank you, team. All right, guys.